welcome to Operating Systems Lecture 2. Yesterday we discussed that software for a computer system is usually very complex. It involves lots of different things, including event handling for devices, running different programs, loading different programs, writing new programs, and so on. And it's important from a manageability and point of view to structure or your system in such a way that it becomes more manageable, and that's in some sense the area of operating systems. And we discussed that an operating system is in some sense the lowest layer of software that sits on top of hardware, and it exposes certain APIs or interfaces to the applications so that they can use those interfaces to do all the things that they would want to do. And we said that in general, designing such an API is not trivial. It's a little complex. And we started with looking at one particular operating system, Unix, which was one of the first very successful multi-processing operating systems, and on which many current operating systems are modeled. And we started looking at what its interface is. Right. In particular, we started looking at one powerful program called shell, which a lot of us use in daily life, and see how a shell is implemented on top of Unix abstractions. Right? And so we said, look, the shell is actually implemented as this loop, which is denoted by the while statement. In this loop, the first thing it does is writes to its file descriptor number 1 a string of length 2. Right? That's the dollar prompt that you see on your screen. The file descriptor 1 is a special file descriptor which points to the standard output. The standard output could have been opened by the shell itself, for example, or it could have been inherited from its parent, or whatever other ways the file descriptor could have been initialized. Moreover, this file descriptor could point to a file, it could point to a device, it could point to the network. So that allows you to write fairly environment agnostic code when you're coding something like this. So the same shell can execute both on a serial port and can execute on your screen. Then there's this imaginary function that I've written here. It's called read command. So you can imagine. So what this read command function does is it invokes the read system call. Right. Once again, as a reminder, a system call is a function that a kernel provides to an application. Right. So inside the read command function, it must be calling the read system call, and it's calling the read system call on file descriptor 0. Right? The file descriptor 0 is also a special file descriptor which refers to the standard input of the program, and once again it can be initialized in any way, exactly as it was initialized for the standard output. It reads commands from the standard input, parses them into these strings called command and args. You can imagine that this command is an array of characters, and then arguments is also an array of strings, where each string is an array of characters. So once it has parsed the command from which it has read from the standard input of the shell, it needs to actually execute that command. Right? So let's assume that the command is the name of the command can be passed as the name of a file on the file system, and so what you're going to do is you're going to execute that file. You're going to pick up that file from the file system and you're going to execute it. But once again, you cannot just execute a file in the context of your own process. So the shell is running in a certain container, which we call the process, which is again an abstraction that Unix provides. And so the way it works is that Unix allows you a system call called fork, which clones the current process. So which means it makes a copy of itself and creates another process which we call the child process. The new copy of the process is identical to the parent process, except that its process ID is different and the return value of the fork system call is different. Right? So we assign the return value of the fork system call to this variable called PID, which is our own local variable, and then we check its return value. If that return value was 0, it means that we are currently executing this code in the context of the child process. In which case, we execute another system call called exec, which takes the command and the arguments and tells the OS to execute this command in the context of the child process. So the parent process remains completely unaffected by this operation of exec, which executes only in the child process. The semantics of the exec system call are that it will completely forget about the current process in the terms of the memory contents, load the executable into the context of the current process, and start it running. Right? So in other words, once you call the system call called exec, control actually never reaches this point, right? Because once you have called the exec system call, you have loaded the new executable, you have transferred control to the first instruction of that executable, and that executable has completely forgotten the context in which it was loaded. Right? So the process is completely sort of reinitialized in some sense. All right. Okay. So you could write anything here, but it will not get executed. Right? That's the semantics of exec. Exec never returns. Right? But an executing process or any process can exit. Right? So there's another system call called exit, which is right. This is again a system call or a function provided by the kernel that a process can call, and the semantics of the exit system call are that the process will terminate, right? And all the resources belonging to that process will get freed, right? So all memory, etc., will get freed, whatever belongs to that process. So that's the semantics of the exit system call. Often, when a parent spawns or forks a child process, it was also interested in what happened inside the child process, whether the execution of the child process succeeded, whether it failed, or what was its return value, for example. Right? So Unix allows you to specify an argument to the exit system call, which let's say called the exit code, or which is just an integer which can be thought of as a return value of the process as it exits. Right? Okay, and the parent. So that's how the child executes. It calls the exec system call, and the program that's loaded inside the exec system call may or may not call exit at some later point of time. The parent can monitor what's happening to the child by calling the wait system call. Right? So the semantics of the wait system call are, in this case I'm calling it with the argument 0. It basically means wait till any of my children exits. Right? So as soon as this child, so in this case, a parent will only have one child at most living in the system, right? So the shell process is one process, and you will only fork and then you will wait. So at most you'll have one outstanding child in the system, right? And so when he calls wait 0, you're basically waiting for that particular child that you just spawned. So wait, the semantics of wait is that it will block till the child is running, and it will return as soon as the child exits. Further, the return value of wait is the exit code that was passed as an argument to the exit system call in the child. Right? So if the child called exit with return value 10, then the return value of the wait system call in the parent will return 10. Right? So that's a limited way of inter-process communication between the child and the parent. Right? There's a question. So what happens if the child does not call the exit system call but crashes? For example, it touches illegal memory and causes a segmentation fault. Right? Even in that case, the wait system call returns with the appropriate error code indicating what happened to the process. So either either you will get the exit code inside the return value, or you will get a special code which indicates that the process crashed and why did it crash. So the parent can get that kind of information for its child. It's a limited form of what I call inter-process communication. IPC, inter-process communication. Once again, if I were to draw the diagram of the OS, this is the OS, this is, let's say, the hardware, and these are different processes, process 1, process 2, and so on. Right? These processes are making system calls to the OS and getting answers to the system calls. Okay? One of the system calls is the fork system call, which actually creates another process here, right? Such that it's identical to the original process that was created. All right. These processes are more or less isolated from each other. So if I'm, if I instantiate a variable here and I write something to it, it's completely in my private space as opposed to a variable that's instantiated in this particular process. However, often you need to communicate between these processes for various reasons. And one way to communicate is what we saw is the exit code between the exiting process and the waiting process. This form of inter-process communication is very limited because it can only be used between a parent and a child. I cannot use it for any two arbitrary processes. Right? Also, it can only be used if the child exits. Right? So it's a limited form of inter-process communication, and it only is useful when one of the processes has actually exited. All right. We're going to see more types of inter-process communication very soon. Anyways. So exit code is going to tell you what happened to the process, the child process, and most shells would typically have an option which say whether you want to display the exit code with which the process actually, your command actually, whether your command succeeded or failed. One of the standard conventions on Unix, for example, is that if a process execution succeeded, then it will exit with exit code 0. If it failed, then it will exit with exit code 1. Or it can or some non-zero exit code indicating the failure condition. Right? Okay. And this third if condition is what? So if the returned value of fork was 0, which means it's a child. The second one was if it's greater than 0, which means it was parent. And the remaining one is when it's less than 0, which indicates error in the fork system call. So the fork actually never happened, right? If the return value of fork is less than 0, it basically means that the fork never happened for whatever reason. Right? There can be many reasons. For example, the process ran out of memory. So this kind of interface, though seems rather easy right now, was actually not so trivial to come up with when it was first envisaged, right? So there were many iterations before on what this right interface should be, before Unix was actually became popular. And as you can see, this interface of so this interface really involves something like a fork system call, an exec system call, the ability to name file descriptors, and to be able to call open, read, write, close on these file descriptors, the exit system call which returns an exit code, and the wait system call which allows you to wait on an exit. And all these things, what they allow you is composability. So it allows you to compose one program inside another program, able to spawn another program and treat it just like a function call, for example. So you just spawn another program, let it run asynchronously, collect its return value, it sort of becomes an asynchronous function call. You can also pass arguments to that spawn process by so specific arguments to that spawn process, by saying what the file descriptors are going to be. You can initialize the standard input, standard output, standard error based on what you want it to be, and that sort of gives you a very nice composable setup, and allows you to treat programs as tools which can be composed and fitted in any place, in any environment that you like to. So in that sense, it was it makes things very clean and useful. In fact, most operating systems today have some flavor of this kind of an interface. We also saw how if I wanted to redirect certain file descriptors to other resources than what shell is currently using, then I could do that by inserting appropriate code before the exec system call inside the child container. right? So for example, when I fork something, the semantics of fork are that the entire file descriptor table of the parent gets copied into the child, right? But if I wanted to say, I want to redirect the output of my child process to some file, let's say, then what I'll do is I will close the existing standard output, and then I'll open the file, and once again the semantics are that open will return the first available file descriptor in the file descriptor table, which means standard output will get reinitialized to file, and now exec of ls can take place. Notice that in this I didn't have to change the code of ls at all. Ls was, it's composable in that sense because I just changed the environment and then invoked ls with that new environment, and now ls behaves as exactly as I wanted it to behave, right? So one interesting example of composability. This, notice that this is possible. This way of redirection is made very easy because I've separated this process creation into two system calls. One is the fork system call, and the second is the exec system call. And now I can do some things in the middle between the fork and the exec system call. It's not very clear why this is a very interesting choice, really, right? Because you may argue, well, it's a little wasteful to do things in this way, because I first create a copy of myself using the fork system call, and then override the copy with something else, right? It seems wasteful that I'll first copy the entire contents and then completely overwrite it with something else. So the first copy was really not needed, and why am I doing it? I'm doing it because Unix allows, that's the only way Unix allows me to create a new process. So it seems it's like it's a performance problem. However, as I've discussed so far, it gives you a lot of flexibility, right? Because you can do things between fork and exec. In fact, Microsoft Windows does not do things in this way, right? So it doesn't do fork and exec. It has this system called create process. So I guess the Microsoft Windows engineers, OS engineers, felt that the fork system call is too costly, and we don't really need to do this. And so they have a system call which says create process, which takes, let's say, a command and arguments. And the semantics of the system call are that it will start a new process and start this command in that new process. So there's no fork, right? So there's no copy being done, and so you're avoiding that wasteful operation, so-called wasteful operation on Unix. Right? However, as you can imagine, the new command may need different types of environment. For example, if I wanted to implement shell redirection on something like this, there's no clear way of how to do it, right? So if I wanted to say ls greater than file foo, not quite possible unless I change the code of ls. So what they did was they added more arguments here, like file descriptors, and so on, environment variables, and so there are roughly 10 arguments in this system call. So so this Windows system call says create a process with this command and these arguments and this environment, right? So that makes your system call rather bulky, but arguably it's perhaps more efficient than Unix. Okay. So there's an interesting trade-off. I mean, so here's an example of a trade-off between clean interfaces, small interfaces, and performant interfaces. It turns out that Unix in its fork and exec is not all that costly. Right? As we're going to discuss later in the course, it's possible to implement fork in a very fast way, right? Using what are called copy on write optimizations, where when you create a new process, you don't necessarily copy the entire process upfront, but you just create pointers to the original process and set the entire process in read-only mode, and only copy when something is written in the new process. In the common case, when the new process actually just execs to something else, your fork was pretty much free. Right? All right, so interesting example of two real-world operating systems doing the same thing in different ways. Okay, last time we saw how shell implements redirection, right? So the way it implements redirection is that before it calls exec, it closes the standard output, close one, and then let's say opens foo, in, let's say, write mode, and then calls exec, right, whatever command there is. And so that gives you redirection of commands on the shell. Right? I could also do something like sh less than foo greater than bar, right? And let's say this is the dollar sign. What it's doing is it's redirecting the standard input to foo and redirecting the standard output to bar. And you could do it in pretty much the same way as we discussed earlier. You will close the standard input, open foo, close the standard output, open bar, and execute sh. Right? If I wanted to execute a shell script, all I need to do is, let's say this is my foo file. It will have, let's say, a few commands, echo 1 and echo 2. So now foo can be a shell script, and when I say shell is less than foo, this shell script gets fed as input to my shell, and that gives you shell script execute, right? So very composable. Here when I said echo 1, I didn't care about where the data is going. I'm basically saying I want to write it to standard output, and the standard output was actually initialized much later in the invocation of the shell script foo, right? So when I say shell sh is less than foo is greater than bar, it basically executes this shell script and prints 1 and 2 on the shell in the file bar. So let me just draw the file descriptor table once again. So let's say this is a process P1, this is another process P2. There's a file descriptor table that's associated with the process P1, and there's a file descriptor table associated with process P2. All right. The process P1 can only access this file descriptor table using system calls. So a process P1 cannot just access this table directly. This table is sort of hidden from the process, and the only way it can actually manipulate or read these tables is using read, write, open, close system calls. This entry, a single entry in this file descriptor table, points to a structure which says where is my resource, and then it says what's the offset of that resource. Okay. So the offset is maintained inside the structure. So let's say the resource is a file foo, and then there's an offset inside the structure which says what's the current pointer at which this file is writing. So when I call a system call like write on file descriptor 1, it basically just starts writing at the current offset off. If there's another file that wants to write, it's again going to write append. So it's going to have, so off is going to get incremented on every write system call. Right? That's how, two successive writes give the feeling of appending to the file. Right? Because off, so that's also part of the semantics of the write system call, that the offset gets incremented on every system call, be it read or write. Now let's say, okay, and one thing I wanted to point out is, so when a process P1 forks a process, let's say it fork P2, then the file descriptor table gets copied, all right, and these pointers are shared, right? So the same structures get shared, and this allows you to do what's called file sharing, right? So the child could be writing to the same file, and the parent could be writing to the same file, and their outputs would now get intermingled in any arbitrary order depending on the execution order. You could insert synchronization between your child and the process to decide the order in which you want to write to this file, but in any case, this implements file sharing. Here's another way of inter-process communication. A process forks another process, the file descriptor table gets copied, the file gets shared, whatever one process is writing is now visible to the other process for reading. Okay. However, if process P2, let's say, calls close on file descriptor 1, that has no effect on the file descriptor table of process P1, right? Because the file descriptor tables themselves have been copied. It's just the pointers that are being shared here. Right? So if this process P2 calls close, absolutely no effect on process P1. The shell also allows you to do something like ls a b greater than file foo, and so this means redirect the standard output to file foo, and 2 greater than file bar, which means redirect the standard error port to file bar, right? That's it, very easy, and you can imagine how this can be implemented. But what it also allows you to do is it allows you to redirect standard error port to the standard output port. So basically saying redirect the standard error, whatever is written to the standard error, to the same resource that's being pointed to by standard output. So that's the syntax for that on shell is 2 greater than and 1. Depends on different shells, but let's say this is syntax for redirecting standard output to standard error. All right. So how would one do this? How would a shell implement this? Well, one naive way to implement this is to do the same thing, which is close 1, open foo, close 2, open foo. Right? Seems like a correct way of doing things. Right, let's see what happens. Here's the file descriptor table. So when you call close 1 and open foo, this gets initialized to foo and offset 0, and when you call open and open foo, this gets initialized to foo and 0. Right? And now when the program calls write on standard output, it's going to write to file foo at a certain offset, and then write something to standard error, it's going to write foo, and now what's going to happen is that they're going to overwrite each other. Right? What you wanted in this command was that they should get appended, right, not overwritten. Right? So what do you need? It would have been nice in this picture, instead of having something like this, I had something like this. So they have a shared offset, and each time they write either to standard output or standard error, the same offset gets incremented. Right? The current set of system calls that we have discussed so far don't allow this kind of manipulation of the file descriptor. So Unix has another system call called dup. Which basically means that duplicate this pointer in the file descriptor table. Right? So the way I'm going to implement this is I'm going to say close 1, open foo, close 2, and instead of saying open foo, I'm going to call dup 1. Right? So that's going to have the desired effect of having a shared offset between standard output and standard error. Okay. Now let's look at more interesting Unix abstractions. So let's say I have a file called file.txt, and I have a utility which takes the file and sorts it. Right? So let's say there's this utility, there's a program called sort, just like there's a program called shell and there's a program called ls. There's a program called sort which takes input from its standard input and sorts it and prints the output to the standard output. Right? Let's say what I wanted to do was I want to first sort all the strings in this file called file.txt. Then there's a program called unique, which takes a sorted file and eliminates all duplicate entries from that. So it just retains the unique entries in the file. So one way to do this is I sort file.txt and redirect it to, let's say, some file temp1. Then I unique and call unique on temp1 and redirect it to temp2. Right. Then let's say I wanted to count the number of unique words in this file. So there's another command called wc with word count, and then I want to say word count less than temp2, or let's say I just say let's say word count less than temp2. Right. And so this the combination of all these three commands is going to count the number of unique words in this file called file.txt. I'm going to first sort the file, find the unique elements, and I'm going to count the number of unique words. Of course, I've created 2 extra files in this process, so maybe the last thing I need to do is remove temp1 and temp2. Right. This kind of a thing is also very common, where the output of one program needs to be fed as input to another program. Right. This is once again very consonant with the concept of tools, where there are multiple tools and you want to say I want to use this tool and then feed the output to this tool and then this tool and so on. Right. If I'm doing it in this way, let's say my file is hundreds of gigabytes or terabytes large. I need a lot of temporary space to be able to maintain this information, number one. Number two, I'm writing extra things to the disk, and writes to the disk are generally costly, and so I'm making things very inefficient. I'm first writing the whole thing to the disk, I'm reading the entire thing from the disk, then writing another set of data to the disk, and so on, and this is all very expensive. Ideally, what should have happened is that I should have had a way on my operating system to specify that here's a program sort, connect its standard input to file.txt and connect its standard output to the standard input of unique. Right? And then connect the standard output of unique to the standard input of WC. And connect the standard output of WC to whatever is the standard output of the shell. Right? Because you basically saying, just let's say the shell was executing on the console, you want the output on the console. Right? So if I was able to do this, if I was able to specify this, then it would be very nice, because I don't need these extra temporary space and I don't need extra temporary time to create these space. Right? So once again, this requires manipulation of the file descriptor tables in certain way, and once again, I can a process is not allowed to manipulate the file descriptor table in any way it likes. By the way, why isn't a process allowed to manipulate its file descriptor table in any way it likes? For security reasons. You're basically saying that these file descriptor tables are referring to shared resources like the console, the file system, the devices, and the OS needs to interpose on any request made to these resources. Right? So the OS will check on an open whether this process is actually authorized to access this device. For example, if this process is being run by the root user, then it can access certain devices, whereas if it's not running as a root user, it cannot access certain devices. So there are ways, so the OS needs to provide gates through which a process can enter. The process cannot just walk over my file descriptor table any way it likes for security reasons. But now now the OS is basically, the OS designer is basically choosing the right set of system calls such that the processes are still able to do what they need to do most of the time. Right? Okay, so I want to be able to do something like this, and and this connection between one file, the output file descriptor on one and the input file descriptor on another, is facilitated by a system call pipe. Right? And pipe was a very new concept that Unix introduced, and very successful since then. Right. So let's see what pipe does. A pipe is a one-way communication channel. Right. So here's an example. Let's say I create an array, which is my FD array of size 2. So there are 2 FDs in this array, and I call pipe on FD array. So this is the syntax of pipe. I'm supposed to call the pipe system call on an array of integers of size 2. And what it's going to do is it's going to create 2 file descriptors in my file descriptor table, and put the output end of that file. So what it's going to do is it's going to create a pipe inside the OS. Once again, this pipe is inside the OS, and the process cannot just access it directly. It has to access it through gates, which are system calls. It creates a pipe, and it assigns 2 file descriptors to the 2 ends of the pipe. Right. So for example, it just, let's say this is the file descriptor table. This is the file descriptor table. What's going to do is it's going to find the first 2 available file descriptors in this table, once again walking from the top. Assign the first one to the input end of this file, and assign the second one to the output end of this file. Right. So let's say the 2 file descriptors that were available were 3 and 4. So 3 is going to point to the input end of the file, or to the okay, depending on, so let's take this pipe as the entity. So the output end of the file is the first one, and the input end of the file is the second one. So with that in mind, if this program says pipe FD array, and then it calls write on FD array 1, let's say it says hello, string of length 5, and then it says read FD array 0 in some buffer buff, let's say its maximum length is whatever 100, then what I'm going to get is answer 5 and the string hello written inside buff. So what has really happened is when you called write, it wrote 5 bytes on this file descriptor, which meant 5 bytes were stuffed into this pipe, and when you called read on this file descriptor, these 5 bytes were read off the output end of this file. Okay. What you've done is, so recall that file descriptors point to resources. So far we have considered resources which are either externally facing devices like console or serial port, or they are files in the system, which are again, so there's a file system, let's say. Here a file descriptor is pointing to an internal resource, which is a pipe that's created using the pipe system call, right? And both ends of this resource are internal, right? In the case of a console, the output end was in the OS, so the input end was in the OS and the output end was on the screen. But here the input end is also in the OS and the output end is also in the OS. That's one way to think about it, right? So when I write to the input end of this pipe in FD array 1 and then read from the output end of this file, I get what I wanted to, I get what I wrote. But this doesn't sound very interesting. I mean, if I just write and then I read, what's the point of doing this through a pipe? I could have just done it internally. I didn't have to involve the OS in this doing this. But what this allows you to do is allows you to do inter-process communication across processes. So as you can imagine, if I call the pipe system call, I have initialized my file descriptor table in this way, and then I call the fork system call, the file descriptor table gets copied to my child, but the pointers remain the same. So they still share the same pipe. And now if the parent writes to the input end of the pipe, and the child reads from the output end of the pipe, you have implemented inter-process communication. Right? So let's see how this works. I could call pipe FD array. This is going to create a pipe, right? Then I'm going to say fork. This is going to duplicate the file descriptor table. Once it duplicates the file descriptor table, the pointers get shared, so the pipe gets shared, right? Then I can say if PID is greater than 0, which means I am the parent, I write to FD array 1, hello, right? And else, if I am the child, then read FD array 0, buff, whatever, 100. Right? In this case, the parent writes to the pipe and the child reads from the pipe. Right? Now, everybody, any questions at this stage? Everybody understands? I created a pipe, I forked after creating the pipe, which means that the pipe now gets shared. Let's just see what happens. Here is process P1, here is the OS. The process created a pipe, so the pipe gets created inside the OS space, which means it cannot be accessed directly by the process, but it can be accessed using read and write system calls. Then this pipe has pointers which are represented by file descriptors. So this is, let's say, FD array 0, and this or FD array 1, and this is FD array 0. Right? Everybody is with me at this point? At this point, the process P1 calls fork, which means another process gets created, P2. The file descriptor table also gets copied, which means that even this process has file descriptors which point to the same file, the same pipe. So now, if this process writes to the input end of this pipe, either P1 or P2 can read from this pipe. They call, so one way to use this is for P1 to call write on the write here, and P2 to call read here, and that way you can pass information between P1 and P2. Okay, all right. So let's look at the example that we had earlier. I wanted to create pipes between sort, unique, and WC programs, right? And so I wanted a picture something which looked like this, right? File.text, sort, standard output connected to standard input of this, and so on. And so one way to do it is you call pipe on FD array, then you call fork, right, and then you say if PID is equal to 0, which means I am executing in the child context, then close the standard output. I want to connect the standard output of my child to the standard input of some other process, right? So what I'm going to do is I'm going to close the current standard output of the child, and I'm going to call loop on FD-array 1. What it's going to do is it's going to copy the file descriptor value in FD-array 1, the pointer in FD-array 1 to standard output. So now the standard output is connected to the input end of the pipe, right? FD-array 1 was the input end of the pipe. So when I did close 1 and the loop of FD-array 1, I've connected the standard output of my current process to the input end of the pipe, right? FD-array 1. All right. And then at some point I can say exec command. Let's say exec sort. Right? I'm hiding a lot of syntax. Let's just understand how it's working. Right? When you execute sort is going to write to its standard output, and the standard output happens to be a pipe in this case. Right? Separately, I will connect the standard input of the other process that I'm going to fork unique in, and I'm going to connect the standard input to the other end of the pipe, and that way I'm going to have a communication between sort and unique. So the syntax for this on shell is sort less than file.text pipe, and this is the pipe character on the keyboard. I think it's and then it says sort and then says unique, and then again pipe and WC. Right? This does exactly what we saw earlier, which means the sort is going to take input from file.text, pipe it to this pipe the standard output to unique. Unique is going to take the input from the pipe and pipe its standard output to WC. WC is going to take its input from the pipe and pipe this and print the standard output on the console. And what I want you to think about after you go back is how the shell will implement this syntax. So this is the syntax that's provided by the shell. It's implemented by the shell using the pipe system call, right? And I want you to write code to be able to do that. Right? It's going to be something very similar to this, where you create a pipe, you fork, and inside the child you manipulate the file descriptor so that its standard output now points to the pipe, and then you exec the program that you wanted to execute. All right. So when I created a pipe, so this is the pipe. Sort is writing here, and let's say unique is reading from here. What happens? So now there's an interesting scheduling question that comes up. What happens if sort gets to execute a lot and unique hasn't even started? Right? So now sort is just producing a lot of data, and unique hasn't gotten chance to run. Right? So now that brings you to the question: how fat is this pipe, or how large is this pipe? So there are default values to the size of this pipe. And always there will be a producer in this pipe, and there will be a consumer in this pipe. If the producer is producing too much and the consumer hasn't even is not consuming at the same rate, then eventually the pipe will get full, depending on the size parameter, and the size is typically in few tens of kbs, let's say. So once the producer gets full, the operating system can figure this out, because the only way a program can produce is using the write system call. And so the operating system sees the write system call. It says where it's going to write. It's writing to this pipe. It figures out that the pipe is full. It says let's block this process. So when it blocks this process, it basically means this process will now not get a chance to run till the pipe has more space. So that makes things more efficient, right? So in a way, now sort and unique programs can now dance together, right? So sort produces something, gets suspended, unique gets a chance to run, unique consumes, pipe gets empty, unique gets suspended, sort runs again, sort unique, sort unique, sort. Right? If the file buffer was very small, you will always have this kind of a scheduling pattern: sort unique, sort unique, sort unique. If the buffer was larger, then it can absorb more things. So they can have it happen in any arbitrary order. It can be sort, sort, unique, sort, sort, unique, 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 sort, whatever. Right? So this way of doing things is firstly more space efficient, secondly more time efficient. You don't have to write anything to disk, and it also gives the operating system nice insight into the scheduling, the right kind of scheduling that should happen for the system to execute at full throughput. Question?
So does the operating system resize the size of pipe?
So it may or may not. That's just an optimization, even if it does. Right? So the user can control the size of the pipe. There's a maximum limit that the size of the pipe can be. Pipe on current operating systems are implemented in memory. So an operating system does not typically use the disk to implement the pipe. So if the pipe is being implemented inside memory, you are automatically bound by the size of the memory, number one. And actually much smaller than that, because you want memory to be available for other things too. So pipes are typically much smaller than what you could have if you had implemented them in disks. Question? Okay, so what if the pipe is so small that even one write cannot complete properly? That's no problem. The semantics of write are that till it writes the entire data, let's say the semantics of the write are till it writes the entire data, it blocks. Right? So if you wanted to write 100 bytes and at 50th byte it got blocked, it just gets blocked. And now the other process some reader should actually wake up, if any. And if it wakes up, it's going to consume. And so the write hasn't yet returned, and yet scheduling transfers are taking place. Right? So scheduling transfers are not necessarily demarcated by execution inside the application. Scheduling transfers can happen in the middle of the execution of a system call. Question? Okay, interesting. So unique is giving its output to word count, and word count is supposed to compute the count of the entire file. And if it has just received half the word count, then what does it mean really for word count to, word count can't really work. So the way word count program must have been written is that it's going to read the input till it reaches end of input, and then it's going to compute something on that input. Right? So till unique is producing something, word count is consuming something. Word count will never produce anything till it has seen the end of input marker. Right? So in this case, unique. So sort is producing for unique, and unique is producing for WC. And these programs could be written either in either in online fashion, which means I read few hundred bytes or few thousand bytes or few million bytes, and then I can compute something on that. Or they can be written in a way that I want the entire input, and only then I can compute something on that in their own application space. Right? So they have allocated buffers in their own application space. They're going to store it in their application space, and now they're going to compute on it. Just like you write a normal program, right? You read from a file, you store it in an array, then you compute something on the array. So instead of reading from the file, in this case you're reading from the pipe. Question? So read will only return values that have ever been written to the pipe. It will never return any unnecessary garbage values, right? And it will return the values in exactly the same order in which they were written to the pipe. So read will never return any wrong value, really. And if you say I want to read the next 1000 bytes, till 1000 bytes are available, let's say the read blocks, right? Or it returns saying I haven't been able to read, I've only been able to read 2 bytes, and here are the 2 bytes, and now it's up to the programmer to say, give me the next 998 bytes. Right? How does the OS release the resources for the pipe? Interesting question. Anybody? There's a system call that we discussed. Close, right? If you close the ends of the pipe, if all the processes in the system, so a pipe is associated with the file descriptors of certain processes in the system, right? If you can figure out that all the ends of this pipe are closed, so no process in the system actually points to this end of this pipe, and the pipe is empty, then you might as well just completely release the resources, because if somebody calls read on that pipe, you can just say that you can block it. You can say nobody is going to write to it. There's no writer to it. So the pipe, one end of the pipe is completely invisible to the system, and so at that point you can release the resources, for example. Okay, good. Okay. The next, so pipe is a very interesting Unix abstraction. The next abstraction I'm going to talk about are Unix signals, and we're going to do this in the next lecture. Okay.